Let's derive a formula for the number of new regions that we create in our circle. Let's say we have this circle with two intersecting lines. The number of regions in this circle is 4. Now let's add a third line. This third line is going to create two new intersecting points. We'll let P be the number of new intersecting points. So in this case, P is equal to 2. The number of regions in this circle with 3 lines, we'll start with 4, what we originally had, and we add on 3, which is 2 plus 1. Now instead, let's let P be equal to 1. So with our two original lines intersecting like this, when we add our third line this way, it will only create one new intersection point. So we start off with 4, the number of regions we had originally, and we only add on 2 more, which I'll write as 1 plus 1. We'll repeat this and see if we can find a pattern. Let's add 2 more intersecting points to this circle. Here they are. And we'll count our regions in a circle with 4 lines. We had 7 from before, and we'll add on 3 more regions. I'll write this as 2 plus 1. Let's add 2 more intersecting points to this circle. So that's down here. Here the number of regions with 4 lines is going to be 6 from before, and we add 3 new regions, which I'll write as 2 plus 1. So the number of regions in our circle will be equal to the number that we had before, plus the number of new intersections generated by the next segment, plus 1. In the disk in our problem, our new intersection points will come from 2 places. They will be generated when our new segments intersect the 2 diameters that are on the disk, and they'll occur when a new segment intersects with one that's already on the circle. So we're going to find the probability that we generate an intersection every time we put down a new segment. Let's let S be our first segment that is already drawn on the disk. And we'll let T be the second segment that is new on the disk. And we're going to find the probability that S and T intersect. First, we'll do casework on the nature of our first segment S. S can either join opposite quadrants. So if we label our quadrants of our disk in the usual way, an example would be if S joins a point in quadrant 1 with a point in quadrant 3. Case 2 is if S joins what I'm calling adjacent quadrants. For example, S joins an endpoint in quadrant 1 with an endpoint in quadrant 2. Now we'll have subcases depending on the nature of T. So case 1A has that T shares exactly one quadrant with S. So if S joins quadrants 1 and 3, it's going to also join quadrant 1 or quadrant 3. So for example, it can join quadrant 1 and 2, or 1 and 4, or 3 and 2, or 3 and 4. Our second mutually exclusive case is that T joins 2 quadrants that are not shared with S. So in this case, T would join quadrants 2 and 4. And lastly, T can join the same quadrants as S. So 1 and 3 again. The subcases will be similar here. Here T again shares exactly one quadrant with S. So for example, T can join quadrants 1 and 3, 1 and 4, 2 and 3, or 2 and 4. Case 2B again has that T shares no quadrants with segment S. In this case that would be 3 and 4, or T shares both quadrants. Same as S, 1 and 2. We'll find the probabilities of all 6 of these outcomes, starting with 1A. Here, our first segment S is going to join opposite quadrants, for example, 1 and 3. Again, these are diagonally opposite on our disk. Here's an example of a segment S. The probability of this occurring, we can calculate by noting that wherever we pick our first endpoint, calling it S1, anywhere on the disk, the second endpoint, S2, cannot also be in that same quadrant. It can be in either 2, 3, or 4, and only one of these is opposite. So the probability that this first segment occupies opposite quadrants is 1/3. In case 1A, we have that T shares exactly one quadrant with S, which again means that T joins quadrants 1 and 2, 1 and 4, 3 and 2, or 3 and 4. The probability of this occurring is one of these 4 possible outcomes. Out of 4 choose 2. We're choosing out of our 4 quadrants 2 endpoints. This reduces to 2/3. Now let's find the probability that S and T intersect. Let's say our first segment is as described up here with S1 and S2 in quadrants 1 and 3. Let's put our segment T over here in the second quadrant, and I'll call this point T2. The location of T2 in quadrant 2 does not determine whether it intersects. If our other endpoint T1 is here above S1, which I'll note like this just means that T1 is sort of higher up in this quadrant than S1 is, then we'll have no intersecting point. If T1 is below S1 in this quadrant, meaning it's further to the right, then we will have an intersecting point. The locations of S1 and T1 are randomly distributed in quadrant 1. Both of them are equally likely to be above the other, so that the probability that we have an intersection is just 1/2. All of these events are independent, so we'll multiply them. So we have the probability that S joins the opposite quadrants, and T shares exactly one quadrant with S, and S and T intersect. We'll just multiply these probabilities. We have 1/3 and 2/3 and 1/2. So the probability from case 1A is 1/9. Now we'll go on to case 1B. Again, we have S joining opposite quadrants. This time, T joins the other two quadrants. We can draw that here. Here is segment S, and this is T. The probability that T joins the two quadrants that do not contain the two endpoints of S. In this example, it would be 2 and 4. That's 1 out of 4 choose 2. And in this case, the probability that S and T intersects is 1. So for case 1B, we have the probability that S joins opposite quadrants. We already found that to be 1/3. Then the probability that T also joins the other opposite quadrants. That happens with probability 1/6. And then the probability that they intersect, that always happens. So for 1B, our probability is 1/18. And we'll go on to case 1C. Again, we have S joins 1 and 3. For example, this time T will join the same two quadrants. This again happens with probability 1/6. Sketching this situation, we'll call the endpoints of S, S1 and S2. Let's draw a segment T that joins the same two quadrants, and we'll call its endpoints T1 and T2 as before. Where S1 and T1 can be anywhere in the first quadrant, S2 and T2 can be anywhere in the third quadrant. So the probability that these two segments intersect, we have that if T1 is higher than S1, as I described before, in the first quadrant, and we have that T2 is lower than S2, meaning it's further down in this curve than S2, or vice versa, meaning T1 is down below S1 and T2 is above S2. Because the locations of these 4 endpoints are randomly determined, T1 is just as likely to be higher than S1 as not, so this probability is 1/2. Independently, either T2 or S2 is likely to be lower. The probability that T2 is lower is 1/2. Vice versa means just the opposite, so we multiply this by 2. So the probability they intersect is 1/2. And the total probability for case 1C, again, S joins opposite quadrants with probability 1/3. T joins the same two quadrants with probability 1/6. And the probability that they intersect is 1/2. This is 1/36. Now we'll go on to case 2. Case 2A has our first segment S joining two quadrants that are adjacent to each other. So for example, quadrants 1 and 2. From part A, we have that T shares exactly one quadrant with S. So T shares either quadrant 1 or quadrant 2, but not both. So T joins 1 and 3, or 1 and 4, or 2 and 3, or 2 and 4. As we showed earlier, the probability that S joins two adjacent quadrants, we can calculate by placing the first endpoint in any of the 4 quadrants. Without loss of generality, we'll just put it in quadrant 1. Our second endpoint cannot also be in quadrant 1. It must be in either quadrants 2, 3, or 4. Only 2 and 4 are adjacent, so the probability that S joins two adjacent quadrants is 2/3. So the probability that T shares exactly one quadrant with S, it's one of these 4 equally likely situations. Out of a total of 4, choose 2 possible ways of choosing 2 quadrants for the 2 endpoints of T. And this simplifies to 2/3. Now let's find the probability that they intersect. Here's our segment S. We'll find the probability that there's an intersecting point between S and T, given that T joins 1 and 4. Note that this probability is going to be the same because of the symmetry of the circle if T joins 2 and 3. Either T joins vertically these 2 quadrants or these 2 quadrants. From an earlier case, you might recall, for example, if T2 is down here, it doesn't matter where T2 is in quadrant 4. It only matters whether T1 is above S1 or below it. These two are equally likely, so this probability is 1/2. Now we can find the probability of an intersection. If t joins 1 and 3, that's going to be the same due to the symmetry of finding an intersection when t joins 2 and 4. We saw something similar to this. Let's put one of our endpoints of t over here in quadrant 3. T2 can be anywhere in this quadrant, but again, it depends on the location of T1. So the probability that we have an intersecting point again is 1/2. So the probability that we get this situation in case 2a, S is in adjacent quadrants, and T shares exactly one quadrant with S, and they intersect. We have 2/3 for this first part. Again, 2/3 for this independent event, the location of T. And in all of these 4 cases, the probability that they intersect is 1/2. So this simplifies to 2/9. We'll keep going to case 2b. S joins adjacent quads. T joins the other 2 quadrants. Sketching this again, that puts S up here and T down below. The probability that there's an intersecting point between S and T, that's never going to happen, so it's 0. We'll go on to case 2c. Here, S and T join the same 2 adjacent quads. We saw this earlier. Again, we had to have T1 above S1 and T2 below S2, or vice versa. This was probability 1/2. So our total probability for case 2c was 2/3 to put S into 2 adjacent quads, 1 out of 6 for T to share those same 2 quadrants, and then 1/2 for an intersection. So this probability is 2c. So now in total, the probability that any new segment in our disk intersects a given old segment is going to be the sum of all of these probabilities that we just calculated. So let's find them. 1a was 1/9. Here's 1b, here's 1c, and then case 2. We have 2/9, this was 0, and 1/18. This adds up to 17/36. So recall from the beginning of the solution, we had a formula for the number of regions in our disk. This is going to be equal to the number of regions that we had previously. We're going to add to it the number of new intersection points, and then we add 1. We also had that there were 2 sources of new intersecting points. Our new segments can intersect with one of the 2 diameters that were originally on the disk, or with other segments that are already on the circle. We always have 2 diameters, so this is going to be fixed. This varies depending on the number of segments that are already on the circle as we add them one at a time. Let's find the expected value of intersections just through the 2 diameters. These diameters are perpendicular to each other. They intersect at the center of our disk. To make this calculation, let's put our first endpoint of our new segment in quadrant 1, so somewhere here, and we'll calculate expected values depending on which quadrant S2 is. So for example, if S2 is in quadrant 2, then this expected value we calculate by calculating the probability that S2 is in quadrant 2 times the number of intersecting points. S2 appears in quadrant 2 with probability 1/3, and the number of intersecting points is 1. If S2 is in quadrant 3, this also happens with probability 1/3. The number of intersecting points is 2, so this expected value is 2/3. Finally, if S2 is in quadrant 4, that's basically symmetric with S2 being in quadrant 2, so this expected value is 1/3. We can add up these expected values, so the total expected value of the number of new intersecting points just through the 2 diameters is always 4/3, the sum of these 3 quantities. This is equivalent to saying that each new segment, on average, adds 4/3 new intersection points just with the diameters. So we're going to add 4/3 for each of the new segments that we draw on the circle. The expected value of the number of new intersecting points between a new segment and all of the other segments, we calculate as 17/36 for each previous segment. So I'll multiply this by n0, the number of previous segments which are already on the circle before we draw the next one. So each new segment adds 17/36 times n0 plus 4/3. These are our new intersecting points, plus 1 new regions. So let's let K be n0, the number of new segments already on the circle. To find the total number of new regions, we're going to start with 4, created by the 2 diameters, and then we're going to add new intersection points, as this K varies, starting with 0 up to 24. When K is equal to 24, we're adding our last segment, the 25th segment. Each time we iterate, the number of new regions is 17/36 times K plus 7/3 4/3 contributes to the number of new intersecting points from the diameter, plus 1 for our formula for the number of new regions. This is 17/36 as k goes from 0 up to 24, and we're going to add 7/3 25 times. Adding up and simplifying these fractions, our answer is 204 regions. If you'd like me to solve any other math contest problems, please leave them in the comments.